complex numbers. We move on from where we stopped in the last class. And then, listen please. And I would like to make a correction to something I taught you in the last class. Which I found out to not correct. Listen. About arguments of complex number. We're talking about the general argument and the principal argument. The principal argument is actually usually an angle between minus pi and pi. It's an angle between minus pi and pi. That means that the angle will go from minus 180 degrees to plus 180 degrees. And of course, it still has the same definition as what we call this, which is said that the island plane, the angle that is mixed with the positive x-axis, okay, going in the clockwise direction, is going to give you this x plus iy. Just pay attention now. The angle formed in the x-axis, so that it's positive in the clockwise direction, and negative in the clockwise direction. Okay, that is still argument. But we want to get the principal argument. It has to be an angle or the value between between minus pi and pi. Okay, so listen. So that means that if I'm working in this upper half of this plane, I'm going to be dealing with angles between 0 and pi. Do you understand that? And if I want to go in this other plane, I have to deal with angle between 0 and minus pi. Does that make sense to you? Alright, so that's the correction of that. So it means that if I want to get the principal argument, I know the general argument can be written as RZ, alright, which is generally given by tan inverse of y over x. And we saw that the principal argument will be written as RZ, okay, which will depend on what you are working with. Do you understand this? Alright, so if you listen, you know that generally we are working with this plane. You can remember your quadrants of angles. You know that in these quadrants, all of the trigonometric ratios are positive. Here, only sine is positive. Here, tan is positive, and here, cos is positive. Okay, so if you are working in this plane, listen. When you have a positive x and a positive y, obviously, you have a positive x and a positive y. Obviously, when you take the tan inverse of this number, whatever number you have here, you're going to have a positive number. When you take the tan inverse, you're going to get a positive angle, which is correct to give you exactly this angle you have here. And also, if you are working in this quadrant, here, you're going to have a positive x and a negative y. That means when you take y over x, you're going to get a negative number. So when you take its tan inverse, you're going to get a negative angle. Is it making sense? Which is also correct because, as you have said, when you're walking down here, you are interested in the negative angle for the principal argument, and up here, you are interested in the positive angle. Does it make sense to you? Alright, so that means that whenever you have x to be greater than 0, this thing is going to be the same thing as tan inverse of y over x. Whenever x is greater than, does that make sense to you? Do you understand that? Because at this side, x is greater than 0. So for this, x is greater than 0, y is also greater than 0. So y over x is positive, the angle is positive as we want it. Okay, for this part, x is greater than 0 positive, y is negative, the angle is going to be negative as we want it. So those will give us direct answers that are correct. Now if you're dealing with this side, okay, at this side you have x to be negative, you have y to be positive, okay? And you actually want a positive angle because you are dealing with the upper half of the plane. Alright, so here you want a positive angle, but when you get your y over x, you're going to have this thing to be negative because y is positive and x is negative. So when you take the tan inverse of y over x right here, what do you think that is going to give you? Tan inverse of y over x. So this this is your x and this is your y in this case. So if you take tan inverse of y over x, that means you have in this case tan whatever the angle is to be y over x, and that means y is going to be opposite the angle and x is adjacent to the angle. Does it make sense to you at all? Alright, so that means that the angle we are talking about is this angle. This is the angle. Y will be opposite. So obviously tan theta here will be equal to y all over x. Is it making sense to you? But that angle will give you a negative answer because you are using the direct value, including their signs. Is it clear? So when you get that angle, then to get this angle that is made to the x-axis, you will have to add 180 degrees to it. We are adding 180 degrees. You know the angle itself is already negative. When you add 180 degrees to it, you are going to get a positive angle that is less than 180. So that will be this angle that you have there. Does that make sense to you? Alright, so you're going to have that to be equal to 5 plus this is tan inverse of y over x. That is what you obtain right here. So, what if you are working in this please listen now. What if you are working right here? How do you go to have here? If you are working in this first quadrant, in the first quadrant right here, you're going to have this to be because if you take tan inverse of y over x, this is your x, and then this is your y. So the angle will have to be opposite this also. So we're going to have something like this. Does it make sense? Do you understand that? So that is going to give you this angle theta. And when you get the angle theta, theta is going to be opposite over adjacent, and theta is going to be opposite over adjacent. So that is going to give us it's going to give us a positive angle. Do you agree with that? Do you understand that? Alright. You know why that's a positive angle, right? So this is going to be negative, and this one is going to be negative. So tan inverse of y over x is going to give us a positive answer. This is a positive answer. But we're in the lower half plane where we want the angle to be negative. So if we want the angle to be negative, then the angle that we're interested in will be this. We want the negative of whatever this angle is. So what is that going to give you? So you can subtract whatever you have here, subtract pi from it. Does that make sense to you? You get that? So that is going to give us, that is, we're going to have tan inverse of y over x, in this case, minus pi. Alright, so this obtains when, in this case, x, so the first one obtains when x is negative and y is positive. So here, x is less than 0, y is greater than 0. Here, this obtains when x is negative, less than 0, and y is also negative, less than 0. Is this making sense? Is this making sense? So that is the idea. Then what happens? What if you have, listen now, what if you have this thing to be, let's say you have x to be 0. What is going to happen? If x is 0, you're going to have, depending on the value of y, okay, you're going to have this thing to be, if y is positive, for instance, you're going to have this thing to be pi over 2. Is it clear? And if this is, if y is negative, you're going to have it to be minus pi over 2. Is it clear? Does that make sense? Alright. If x is 0, that means there is no real part. It is a purely imaginary number. If x is 0, you're going to have that, depending on where y is, if y is positive, then the angle I'm interested in will be the angle between this and this, which will be plus pi over 2. Is it clear? And if y is negative, they're going to have this angle to be this, which is minus pi over 2. Is that clear? Is this clear? Alright, so we're going to have this thing to be equal to pi over 2 when x is equal to 0 and y is positive, greater than 0. And then it's going to be minus pi over 2 when x is equal to 0 and y is negative. Does that make sense to you? That will be the principal argument. So that is what your calculator actually evaluates directly. That's your calculator evaluates. Minus pi and pi. So if I'm coming this way, okay, instead of going, when I'm going this way, it's going to be positive. That's the clockwise direction, the counterclockwise direction. Then coming this way to be negative. But I want the angle to not be greater than 180 degrees in magnitude. Is that clear? Is that clear? We already captured that in the first one. In the fourth quadrant, x is greater than 0. You get here. So that's already captured in this statement. Is that clear? Do you understand that? X is greater than 0 right here, but y is negative. So if you take the tan inverse of y over x, you're going to get a negative angle, which already tells you the angle you have here. Do you understand? Because we want the angle here to be negative. If y is 0, basically, if y is 0, we don't write this as part of the general formula like that. If y is 0, we usually have no business. That's just a real number. You get it? Do you understand? It's not a complex number. But if y is 0, of course, depending on the value of x, if x is positive, you're going to have that to be 0. Happy? And if x is negative, you're going to have that to be 5 or minus 5. Do you understand? Alright, so let's see. X is greater than or equal to 0. This is y greater than or equal to 0. Anyone here, first quadrant, second quadrant, it will be positive. And for those here, third quadrant, fourth quadrant, it will be negative. Do you understand that? Tan inverse of infinity is 90. You get that? Is either 90 degrees or minus 90. That is why these two parts are now added. Do you understand that? So that it's either plus 90 or minus 90. So it will be plus 90. This is y is greater than 0. It will be minus 90. This is y is greater than 0. Does it make sense? Alright. So, and for this, when y is equal to 0, so you're going to have tan inverse of 0. Happy? Did you get that? You're going to have this to be tan inverse of 0, and that's going to be 0, so you're going to have this to be 5. Is it making sense? And then here, you have this expression. If x is less than 0, you're going to have this with this. Alright, so can we move on? Can we move on? Okay. Alright, so we have some questions. You will actually find the modulus and arguments. Was that what you have in the assignment? Okay. So one of those we have solved. Let's do the proper thing now. Find the modulus and argument of minus 2 plus 3i. Minus 2 plus 3i. Find the modulus and argument. Find the modulus and argument of minus 2 plus 3i. Alright. So I want you to do it. Use your head. I said I'm correcting what I told you in the last class. Did you hear that when I started? It's okay. The second quadrant, don't forget here. That's it. You have x to be negative and y to be positive. How do you correct the one? That's going to be equal to this. That's going to be arguments of c is going to be equal to 5 plus tan inverse of y over x. Our y is our x is minus 3. Clear? So if you are using 5, that means you have to get this one in radians. Clear? And if you want to get this in degrees, this should be equal to 180 degrees plus tan inverse of q over minus 3. Clear? X is the real part, y is the imaginary part. Right. So you can do that. What does it give you? 180 Is that clear? Is this clear? Right. So what is going to be the modulus of this? R is equal to the square root of 2 squared plus 3 squared. What does that give you? Hello, listen now, listen. So the test of whether or not you are written the proper thing. Hello, listen please. Listen. Is that when you get these results, you can get the complex number apart from the results. Okay? So this complex number is the same thing as having r cos theta plus I r sin theta. That's r is cos theta plus I sin theta. Okay? So whatever argument you have obtained here, by the time you put it back here, you must get these results. Is it clear? Okay, so this is going to give us something like this now. This is going to be root 30 into plus 123.69 degrees plus I sin 123.69 degrees. You understand this? What does that give us? So we can check it out. How sure you have found the wrong thing, that the right thing is that it has to be an angle between minus 180 and plus 180. Is it clear? And then when you get this thing back, you must, when you take this calculation, you must get the same results that you started. Do you understand that? That's how to check. See that you have written out the right one. So that's that about that. Let's move on. So I gave you an assignment to carry out some division and multiplication. You have to find first one is what? C1 over C2. Alright. Yeah, given Z5, but no reference was made to Z5 in the question. So, the first one is to get Z1 over Z2. And the best way to do this, we know that Z1 over Z2 is equal to R1 over R2. Did you get that? Because in this case, these are 1 minus theta 2 plus I sin theta 1 minus theta 2. Can you remember this result that we obtained in the last class? Can you remember this? So, it's okay, please. So to do this, just get your R1 and R2 and get theta 1 and theta 2. Those will be the arguments of the complex addition of them. So what is going to be our R1? R1 will be square root of 2 squared plus 3 squared. What does that mean? And R2 will be equal to the square root of even if you don't have sense, there are many people in class. Please just pretend that you have sense. So this is going to be minus 2 plus 3 all squared. What does that give you? The first one, root 13. This one is also root 13. So we can get this argument for the first one. That's going to be what? So, theta 1, we know it's the first plane, the first quadrant. Alright, so this is going to be equal to the tan inverse of y over x, that's 3 over 2. Whatever angle you get from that. Then theta 2 is going to be equal to, theta 2 is in which plane? Alright, it's in the second plane, Abby. So this is going to be 5, Abby, plus tan inverse of, let's use degrees. This is going to be 180 degrees plus tan inverse of minus 3 over minus 6. The first one is what? Yeah? 56 second one? 123.69 degrees. So, with this, you can conclude that division of these two. Therefore, V1 over V2 equal to R1 over R2, that's root 13 over root 13 multiplied by cos theta 1 minus theta 2. Theta 1 is 6.3 degrees minus 123.69 degrees plus I sine 6.3 degrees minus 123.69 1. And then what is cos of this? 0 point what's that? Minus 0.92. Alright, so that's going to be your result. Okay? Yes. So listen out. Yeah. So a faster way you could have done this is, why am I using this method? Because that is what the assignment deals with. You understand what I'm saying? The context of the problem is division using this modulus and argument. You understand that? I said the context of the problem. I gave you after having taught you how to use modulus and argument. You understand that? No, it's not from the course now. In fact, nobody can give you this in the exam. How they give you this? This is too simple now. How somebody give you? Won't you feel insulted? I all over minus 2 plus 3i. When you multiply by the conjugate of that's minus 2 minus 3i. All over minus 2 minus 3i. This is going to give you this multiplying this. That will be minus 4 minus 6i. Then minus 6i. And then plus. So this will be minus, right? I square is minus also. So this will become plus 9. Does that make sense? You understand that? Yeah. Alright, here divided by the square of this plus the square of this. That is 4 plus 9. Is it clear? You get that? So this is going to give us minus 5 plus this. That is 5 minus 12i all over 13. This is going to be the same thing as 5 over 13. Minus 12 over 13i. Yeah, but that should be the same thing as yes. It's the same thing. Where are you? Alright, so that's that about that. So let's move on to the next section. You can do others the same way, so there's no issue with this. So we talk about exponential representation of a complex number. Exponential representation. So listen now. So far we have seen that a complex number C can be generally be in the form x plus iy, okay, where y is the imaginary part and x is the real part. We said that if x is 0, that means that the number is purely imaginary, and if y is 0, that means it's a purely real number. So this is the expected form. I will say that you can also have this in polar form. In polar form, you're going to have this thing written as r into cos theta plus I sine theta. So this is the polar form of the complex number. I'll say the modulus and argument form. So r is its modulus, is equal to the modulus of z, and theta is equal to the argument. Usually we use the principal argument of z. Okay. So we can also have what we call the exponential representation of a complex number. So you should recall that last semester we talked about all of this. You can write this in series form, and also you can write e raised to power x in series form. What we add this one to be something like 1 plus x squared over 2 factorial plus x cubed over 3 factorial plus blah blah blah. Abi? Can you remember something like this? Yeah. You can also write sin x and cos x in this form. So what's the form for sin x? You remember that we saw that cos x would be what we call an odd function, and sin x, no, cos x is an even function, and sin x is an odd function. Can you remember that? An even function is saying that when you put in minus 2 or plus 2, you're going to get the same results. Is it making sense to you? Alright, so we get that. Generally, we're going to have this thing to be something of this form. We're going to have this thing to be, please, let me check this. See, I can't remember what this is. So this is oh my God. Plus x is power 5 over 5 factorial minus x power 7 over 7 factorial plus x is equal to it's going to be something like that. That's you get that? And for this, we're going to have this to be 1 minus x squared over 2 factorial plus x power 4 over 4 factorial minus x power 6 over 6 factorial and so on and so forth. So you want to get so you now do e raised to power ix, where I is a complex coefficient, square root of minus 1. Okay, what do you think this is going to give you? Obviously, this is going to give you, what is substitute? That means whenever you have x here, you're going to put in ix. Is it clear? So this is going to give you 1 plus ix plus ix all squared over 2 factorial plus ix raised to power 3 over 3 factorial plus ix. So we got raised to power 4 over 4 factorial plus ix power 5 over 1 factorial plus ix raised to power 6 over 6 factorial plus ix raised to power 7 factorial and so on and so forth. Alright. This is going to give you is 1 plus, please pay attention to this, pay attention now. We're going to have this to be ix still. We're going to have this to be I squared minus, this will become minus x squared over 2 factorial. This will be what? This will be minus I. I raised to power 3 is minus I. Alright, this is going to be minus I x raised to power 3 over 3 factorial. And this one is I raised to power 4 is 1, right? That is going to be plus x raised to power 4 over 4 factorial plus this is going to be I. You get that? That is x raised to power, that's I raised to power 4 multiplied by I. I raised to power 4 is 1. 1 multiplied by I, that is I. It's going to be I into x raised to power 5 over 5 factorial. Does that make sense? And this will be minus 1. Is it clear? That will be minus x raised to power 6 over 6 factorial. This will be minus I, right? That will be minus I. X raised to power 7 over 7 factorial. And so on and so forth. Do you understand that? Did you get this? Alright. So you can now rearrange them. So you see that, listen. The ones that don't carry factorial, you look at the ones that don't carry factorial. You have 1 minus x squared over 2 factorial plus x raised to power 4 over 4 factorial. You see that? And then what else? This one, x raised to power 6 over 6 factorial. Is it clear? You see that those ones are the same thing as the terms you have for the course. Is it making sense? Is that clear? The terms that don't carry I here are 1 minus x squared over 2. Do you get that? 1 minus x squared over 2 factorial, x squared over 4 factorial, minus x raised to power 6 over 6 factorial. Can you see that? So those are cosines. I can put them together. Do you understand that? Those are terms defining the cosine. So this is going to be equal to 1 minus x squared over 2 factorial plus x to the power 4 over 4 factorial minus x to the power 6 over 6 factorial plus blah blah blah. You get that? Plus, then I'll put together those terms containing I. So I'll factorize I and I'll put in what do I have left? X, right? So that is what? X. I have minus x raised to power 3 over 3 factorial, that is it here. Do you understand that? Then x raised to power 5 over 5 factorial, this is it here. Minus x raised to power 7 over 7 factorial. Do you get that? So that would be minus x minus x to power 3 over factorial plus x to power 5 over 3 factorial minus x to power 7 over 7 factorial plus blah blah blah. Is it making sense? So obviously, e raised to power ix obviously now, e raised to power ix is the same thing as cos x plus I sin x. Is it making sense? Do you get that? Alright, so that means that if I have, listen now, if I have cos theta plus I sin theta, it means that I can write it as e raised to power I theta. Is it making sense? Do you get that? So that means if I want to represent this complex number, I know this complex number is z equal to r into cos theta plus I sin theta, and then so I can write this complex number as r e raised to power I theta. Does that make sense to you? That is the exponential representation of complex number. So we want to do, yeah, look at it. We want to get the, listen, we want to get something like this. Pay attention now. We want to get the conjugate of this complex number. What do you think is going to give you? Conjugate of this complex number. V bar. You know that V bar normally should be equal to R into, pay attention please, cos theta minus I sin theta. I will get that please. Please pay attention please. So this can also be written as R into cos minus theta. You know cos minus theta is the same thing as cos theta. I mean, theta is an even function. Cos minus theta is the same thing as cos theta. And I can write this as plus I sin minus theta. I know sin minus theta is minus sin theta. Does it make sense? What I have here is the same thing as this. So basically, I can write this as R e raised to power minus I theta. Does that make sense? Do you understand that? Do you get that? Yes. Whatever you have here is what will be the coefficient of I to the power. Happy? So what do I have here now? Minus theta. That will be the coefficient of I to the power. Does it make sense? Did you get this? So I'm going to get the conjugate of this complex number. I'll write this in this form. R e raised to power minus I. So obviously, as we have seen in the past, if you multiply here, z multiply z prime, or z bar, this is going to give you what? This is going to give you R e raised to power I theta multiplied by R e raised to power minus I theta. So what does that give you? So this is going to give you R squared e raised to power, so this will be I theta plus minus I theta. That's e raised to power 0, right? That will give you R squared, which is the same thing as before. Is it clear? The square of the modulus of that complex number. Alright, so I think we are good to go now. Express the an example.
Chill.
Okay, we should chill. Alright, you have 2 minutes to write that. This is the same thing as I. Is it clear? We start over again. So, as we have multiples of 4, I mean powers of 4, we start from 1. You get that? So that is how it's right. Express the following complex numbers in their equivalent exponential form. Number 1, d1 is equal to 2 minus 2i. d2 is equal to minus 1 plus 3i. So, you know what the problem is here? The problem is to just get the modulus and argument. Abi? Once you get the modulus and argument, just write it in this form. That's all. You get that? Just write it in this one. So whatever modulus you get, that's your R, Abby. Just put R. And whatever argument you get, that's your theta. And of course, here you should always write this in terms of, you should always put this in radians. Do you understand this? When you're writing the exponential form, always put it in radians. Always put it in radians. To modulus R, what is it? R, 2 root 2. Then exponential I, what's the argument? Principal argument. 5 over 2? 5 over 4. Minus 5 over 4. Minus I 5 over 4. Do you understand that? No. Do you know why it is minus 5 over 4? No. I didn't say we should change the 5 over 4. X is still yeah, x is greater than 0. So the arguments, the principal argument is same as the normal argument. The general argument. So your standard inverse of x y over x. So we know that x is positive and y is negative. That means it is somewhere around here. Do you understand that? X is positive and y is negative. That means it is somewhere around here. So you should have a negative angle. Am I making sense? Alright, so that's negative angle. You know that this one is 2 and this one is 2 also. So definitely it should be 45 degrees. Do you understand that? And it should be minus 45 degrees because it's going clockwise. Is it clear? Alright, so you're going to have your arguments that will be minus 45 degrees. Which is what? Minus 5 over 4. Is it clear? In radians. So that's how we think about that. So I can now write that 2 minus 2i is equal to 2 root 2 exponential minus I 5 over 4. That's that. What's the next one? Unit power I 2.8. Kilo quick. 1.89. Yeah, 1.89. Positive, right? Yes. In radius. Yes. 1.89, right? 1.89. Okay. You didn't get that empty on. You didn't get 1.89. Its modulus is what? 3. Right? Then exponential. What's its argument? Pi, right? Yeah. Pi. This is I pi. You get it? This is the calculator, you know it's quite simple. Just use the calculator to get it in modulus and argument from. Then just write this out. Results. Do you understand me? You understand what I just said? Yes, yes. You don't need to add it, yes. I'll give you a straightforward answer. Provided the calculator is original. We saw in the last lab, we saw how to know that your calculator is original. If the calculator is original, you don't need to bother, just put it in, get the modulus and arguments first. And get the modulus and arguments. When you get the modulus and arguments, just write it to this. The power theorem. The mobile theorem. The mobile theorem. I've done that also in MTH 101. That's magic. And I did it in MTH 101. No. Yes. So the mobile theorem. This is a big boy.
Nigga now, what's
Alright, so the Mover's theorem tells us, listen now, it's a theorem that's, the Mover's theorem, hello, listen, the Mover's theorem is used to get the power of the complex number. We have powers of a complex number. You want to evaluate them, you can actually get it using the Mover's theorem. For instance, we have the number z. Okay, the exponential form as r e raised power I theta, which we know should be equal to, please pay attention, this should be equal to r into cos theta plus I sin theta. Then we are saying that if you want to take the nth power of this, z raised power n, obviously should be equal to r e raised power I theta raised to power n. I mean, which you expect to be r raised to power n, e raised to power I n theta, and you expect this to be equal to r raised to power n into cos n theta plus I sin n theta. Alright, this is what we call the Mover's theorem. You see that when you take the nth power of the complex number, it should result in this. That is, just raise the modulus to the power of n and multiply the argument by n. Is it clear? You understand this? Raise the modulus to the power of n and multiply the argument by n. So we're going to shortly examine the proof of this theorem, which is an exercise you have been asked to do. So we're going to listen now. So we're going to prove this by what we call mathematical induction. Have you heard of mathematical induction? No. Alright, so mathematical induction, listen now, hello, listen. We will usually use mathematical induction to show that a mathematical statement is true for all natural numbers. You can remember only by natural numbers. I remember natural numbers. Numbers starting from 0, Abi, 1, 2, 3, positive integers including 0. You get that? So we want to show that this is actually true. And for you to do the mathematical induction, the first thing you want to show is that you show that it is true for n equal to 1. You show that it is true for n equal to 1. Then you assume that it can be generalized for all n. Then you now verify that by showing that it is true for any n plus 1. Okay? When you have completed that, that means you have actually proven that it is true for all natural numbers. Right? So you will do that shortly. You should write down the steps. Are we together? So write down the steps. Steps to prove by mathematical induction. Steps or the procedure for mathematical induction proof. Procedure for mathematical induction or procedure for proof by mathematical induction. Give me the procedure. Alright, number 1. Show that it is true for n equal to 1. Show that it is true for n equals 1. That's number 2. And number 1. Number 2. Assume it is true for n equal to k. Assume it is true for n equal to k. N equal to k, where k is element of z plus. Do you understand that? What's that? Z plus. Positive integers. That is natural number. Have you now? Assume that it is true for n equal to k, k element of z plus. Number 3. Then show that it is true for n equal to k plus 1. Show that it is true for n equal to k plus 1. Full stop. If this is true, if this is true, comma, then the conclusion follows. The conclusion follows that it is true for all n elements of Z plus. Then the conclusion follows that it is true for all n elements of Z plus. So let's take it a step after the other. So we're going to do by mathematical. So please pay attention now. So one of the things that
You go for it.
this is the first part. I want to show that element of Z plus. That means one of the first establish that it is true for n element of Z plus. That means it is true for all positive integers, and that's what we use mathematical induction. Alright, so what's the first step? The first step is you want to find out for n equal to 1. What are we going to get? When n equal to 1, that means we are saying that Z raised to the power 1 it should be equal to R raised to the power 1 multiplied by cos 1 multiplied by theta. Do you understand that? Okay. Plus I sine 1 multiplied by theta. Is it making sense? So definitely this is going to be what? This is going to be equal to R. The R is power 1 is R into. So what I have here, cos 1 theta is written as cos theta. This is written as cos theta plus I sine theta. Is it clear? Okay. Which is what? Which is equal to. Is written as R e raised to the power I theta. So obviously it is true for n equal to 1. Is it making sense to you? When you put n equal to 1, you're going to get back the function as you want it to be. This is what's true. You can write that s is true. So therefore it is true for n equal to 1. That's the first step, right? So the next one is what? We assume it is true for n equal to k. For n equal to k. So that assumption implies that is Z raised to the power k equal to R raised to the power k into cos k theta plus I sine k theta. Does that make sense to you? That's our assumption. So we are saying that Z raised to the power k is going to be equal to this. Alright? So we now want to use this result. We're going to induce this result in the last step. And this is to establish that it is true for n equal to k plus 1. So we now check for n equal to k plus 1. What will happen for n equal to k plus 1? We need to have this to be Z, please listen now. Z raised to the power k plus 1. So Z raised to the power k plus 1 is going to be equal to Z raised to the power k multiplied by. Does that make sense? Yeah. So I can write this as. So I already know, please pay attention, this is where the induction happens. I'm going to induce this result that I already wrote here, I'm going to induce it into this. That means I'm going to put in this result right here. That's what we mean by mathematical induction. That is, if this is true, we want to find out if this thing is true for n equal to k, it is also going to be true for n equal to k plus 1. Is it making sense to you? So if it is true for n equal to k, then definitely 0 raised to the power k should be R raised to the power k into cos k theta k plus I sine k theta. Does that make sense? Okay. So I'm going to have all of this for z then multiply by z. Is it clear? So I know z should be what? R into cos theta plus I sine theta. Is it clear? Yeah. So I'm going to have deal with this. Cos theta plus I sine theta. So, are we together? So we're going to do this together now. This is going to give us what? So here I'm going to have R raised to the power k multiplied by R. That's R raised to the power k multiplied by R. Is it clear? Then then I'm going to have this to be this. I can multiply what I have here. So multiplying this by this. What does it give us? So to open that bracket, I'm going to have this to be cos k theta multiplied by cos theta. So I'm going to have this to be cos k theta multiplied by cos theta. Does that make sense? Is it clear? Alright. Then this multiplied by this, that will be plus I sine theta cos k theta. Does that make sense? Then I have this multiplied by this, that will be plus I sine k theta multiplied by cos theta. And I have this multiplied by this. I times I is minus 1, that will be minus sine k theta. Is it clear? Sine theta. So I'll close the bracket, right? Is it making sense? Yeah. This is going to give us I raised to the power k plus 1 into, so I can rearrange this. Those ones that don't carry I can put them together. And the ones that carry I can put them together. So this is going to give me cos k theta, okay, multiplied by cos theta, minus sine k theta, multiplied by sine theta. Pay attention. Then I'm going to have plus I into, so put this also together, those that carry I. I'm going to have this to be sine theta cos k theta plus sine k theta cos theta. Is it making sense? Yes. So I'm going to have all of this. Right. So we can simplify this expression. Don't forget, you should recall that when you add cos A plus B, cos A plus B is what? Cos A plus B minus sine A sine B. Does that make sense? And then sine A plus B also will be equal to sine A cos B. You know what I'm doing? Alright. Plus this is going to be this case we are going to have this sine cos A. Does that make sense? Can you remember this? Can you remember that? So that's going to give us what? So you can see what we have here is cos k theta cos theta minus sine A theta sine theta. So that's like cos A plus B. That's the same thing as sine cos k theta plus theta. Is it making sense? So therefore, g raised to power k plus 1 is equal to r raised to power k plus 1 is equal to cos, what I have here is cos k theta plus theta, is it clear? Plus I, so what I have here also is what? So sine A cos B, so that's the sine theta cos k theta, sine k theta cos theta. That's going to be sine k theta plus theta. Is it making sense? Sine k theta plus theta. So at the end of the day, I can put this result together. So don't forget, I have a destination in mind. The destination should be that, listen please, listen. I want to show that this expression or this statement is true for n equal to k plus 1. And if it is true for n equal to k plus 1, then I should have z raised to the power k plus 1 to be equal to r raised to the power k plus 1 into cos, in this case, I should have cos k plus 1 multiplied by theta. Is it making sense? Plus I sine k plus 1 multiplying theta. Is it making sense? Alright, so that is my destination. So to arrive at that now, I just need to factorize theta, from this argument, factorize theta from this argument. That will establish that it is indeed true for n equals to k plus 1. Is it clear? Alright, so this is going to give me r raised to power k plus 1 into cos k plus 1 plus I sine. Is it making sense? So that tells me that this statement is true for n equal to k plus 1. Is it making sense? So we can conclude that based on this, I will conclude that. S now conclude finally, hence v to the power n equal to r raised to the power n into cos n theta plus I sine n theta for all n elements of the integral. Is it clear? So that's that about that. But this is true not just for positive integers, it is also true for rational numbers. You know what I mean by rational numbers? That means you can also have it to be fractional power. Let me know when you're done so we can move on. Prove that the De Moivre's theorem. Prove that the De Moivre's theorem. Prove that the De Moivre's theorem is true for n elements of z minus. It's true for n elements of z minus. That means it is also true for negative integers. For n elements of z minus. Alright, so look at this. So in this case, please pay attention. Solution. So here, please pay attention. You can set, in this case, you can set the power equal to minus n. So in this case, you know that if it is true for negative integer, let's say n, let n be an element of plus. That means n is a positive integer. So we want to show that it is true for minus n. Is it making sense? So for z raised to power minus n, we want to establish that z raised to power minus n is going to be equal to r raised to power minus n into plus minus n theta plus I sine minus n theta. Does that make sense? Alright, you're going to complete this yourself. So, starting with this, I want to show that it's going to be equal to this. Is it clear? Alright, so we are going to have this to be z raised to power minus n. So we're going to start with odds. Z raised to power minus n equals to 1 over z raised to power n. Is it clear? You know that this one, you have established that it is true for the positive integers. Is it making sense to you? Alright, so I know that this is true for positive integers, so this is going to be equal to 1 over r raised to power n into cos n theta plus I sine n theta. Do you understand what I'm writing? So, with this, we want to arrive at this at the end of the day. So you know that basically I can bring up the n, that's going to be r raised to power minus n. Is it clear? Then multiply by what I have here, multiply by 1 over cos n theta plus I sine n theta. What is it you are going to do here? Rationalize the denominator. You can rationalize the denominator and see what you're going to get at the numerator and this. Is it clear? Alright, so do that now. I said it was a classwork now. So you have to
example class.
So you recall that cos theta is equal to all over 1. Cos square theta plus square theta is 1. So we're going to have this to be r raised to power minus n multiplied by cos minus n theta plus I sine minus n theta. Is it clear? That's that. Yeah, cos theta is equal to minus cos theta. Cos x is equal to minus Alright, assignment. Assignment. prove that the Mover's theorem, is true for all n equal to p over q, for all n equal to p over q, for all n equal to p over q, where p and q are integers, okay, and q is not equal to 0. Abi? That's the way to ask you to prove it for all rational numbers. Is it clear? Prove that it's true for rational numbers. So in this case, listen, I just want to give you listen. When you have here z raised to power p over q, so you can write this as z raised to power p multiplied by all raised to power 1 over q. Abi, 0 raised to power p is already an integer. We have established already that it is true for all integers. You can write this in the remover's theorem and show that when you raise to the power of 1 over q, it's still going to give you that. Is it clear? So that's about that. I'll see you. I'll see you when I see you on Thursday. Tomorrow we are going to